Hi, this is Dr. Bricker here with some hints for homework number 8, which is over Chapter 7, Rotational Motion. Let's take a look at the problems. Okay, in the first one we have a record rotates on a turntable at 33 RPMs, and you can refer to these pages in the text. What is the angular speed in radians per second? And then secondly, what is the period of the motion? So a lot of Chapter 7 is just knowing what different things stand for, different variables stand for. So let's take a look at this. Okay, so first of all, 33 RPMs, what does that even mean? Well, it's 33 revolutions per minute. It's a frequency, 33 revolutions per minute frequency, but it's just not in SI units. So frequency is how many things happen per unit time. The SI unit would be revolutions per second. So let's change it into SI units. So 33 revolutions per minute, and then we have 1 minute is 60 seconds. The minutes cancel out, and then you have revolutions per, how many revolutions per second. And that's what frequency actually is. Okay, so if you do the math here, it turns out to be 0.55 revolutions per second, and a revolution per second is a hertz, or whatever it is, oscillation, revolution, anything that repeats itself, so 0.55 hertz. What we actually want is the angular speed. Okay, so the angular speed is omega. That's why I say it's difficult. Part of the difficulty is just knowing what these things are. This is angular speed. It's not W, it's omega, and it's measured in radians per second. So it's 2 pi times the frequency. So here it would be 2 pi times 0.55. And that gives you the answer in radians per second. Another way of thinking about it, and this is the way that I think about it, if you have 0.5 revolutions per second, one revolution, if you go all the way around one time, is 2 pi radians, all the way around the circle. And the revolutions cancel out. And then you can really see that we have radians per second. The radians part is just a label. It's not really a unit. So if you do 0.55 times 2 pi, you get this number. That's one way of looking at it. Another way is just to use the formula 2 pi times the frequency. So 2 pi times 0.55. And really it's 2 pi, and again, radians is the label that you don't usually see here. Anyway, you get the same answer regardless of which way you do it. In part B, we want the period. So if you have the frequency, the period is 1 over the frequency. So be careful. In this context, t here is the period, the time to go around one time. So if you have the frequency from part A, which we do up here, then you can get the period. Okay, let's go on to the next one. Okay, so 7.8. A fast-moving superhero in a comic book runs around a circular 70-meter diameter track 5.5 times, so 5.5 revolutions in 3 seconds. What is the speed in radians per second? So the angular speed. Okay, so here's what I know. The diameter is 70 meters, 5.5 times in 3 seconds. So let's see, 5.5 revolutions. And I know 1 revolution is 2 pi radians, and this all happens in 3 seconds. I'm trying to get this to look like radians per second. So 5.5, again, revolutions times 2 pi, radians per revolution. This will give you the amount of radians that you've gone through. Okay, and then to get the angular speed, this would be this many radians. So really this is what delta theta is. I'm just putting it into radians. Revolution's perfectly good, just not an SI unit. And then to get the angular speed, it would be delta theta over delta t. And you know how much the time is here. Just to be consistent, delta t, 3 seconds. Okay, so first of all, get the amount of radians that you've gone through, divide it by the time. That'll give you the amount of radians per second. Okay, next one, 7.13. To throw the discus, the thrower holds it with a fully outstretched arm. Starting from rest, he begins to turn with a constant angular acceleration, releasing the discus after making one complete revolution. The diameter of the circle is 1.8 meters, and we want to know if the thrower takes 1 second to complete one revolution starting from rest, what will be the speed of the discus at release. Okay, let's take a look at this. Okay, so the discus thrower completes one revolution in 1 second. The diameter of the circle that the discus goes through is 1.8 meters. Starting from rest, what's the final speed if we have a constant angular acceleration? So angular acceleration is alpha. We don't know what it is, we just know that it's constant. Good, so I think I can figure out the average angular velocity, because this is just delta theta over delta t. So if you think about omega versus t, if this is increasing at a constant rate, it would look something like this. We can get the average angular velocity, but to get the final angular velocity, we'll have to take the average and multiply it by 2, because really we're starting at rest. The initial is 0. We're trying to figure out the final here. The reason I want to figure out the final angular velocity is once I have that, I can figure out the actual linear velocity from this relationship. So if I can get the final angular velocity, multiply it by the radius, I'll get the final angular speed. Okay, so this is just the average. And if we start at rest, we know that the final is going to be twice the average. Okay, so kind of think about it. If this is the final, this is the initial, the average is in the middle. If you multiply that value by 2, then you get the final angular speed. Okay, so let me recap. We want to get the average angular velocity, which I'll be able to get from the information given. Once I have the average, multiply it by 2 to get the final angular velocity. And really the problem's asking for the linear velocity, and it's related to the angular velocity like this. Okay, so make sure you do this in radians per second, which you'll be able to. You go around 1 time, that's 2 pi radians in 1 second. So you can get that, similar to problems we've already done. Multiply that by 2 to get the final angular speed. And then the final linear speed here is the final angular speed multiplied by the radius. So we're given the diameter, just make sure you turn it into the radius, divide it by 2. Okay? Okay, the crankshaft in a race car goes from rest to 3180 revolutions per minute in 2.3 seconds. Okay, so this is sort of like, this is frequency. It's just not in the correct units. 3180, we wanted it to be revolutions per second, then it'll be a frequency, but that's okay, we can work with that. We want to know what's the crankshaft's angular acceleration and how many revolutions does it make while reaching 3180 RPMs. Okay, let's take a look at this. Okay, so we're given 3180 revolutions per minute, and that's not an SI unit. I've got to turn it into revolutions per second, which I can do. Then that's the frequency. This happens in 2.3 seconds. Starting at rest, we can figure out what the final angular speed is. It's take the frequency, multiply it by 2 pi. So you'll have the initial, which is 0, the final after a little bit of work. And then angular acceleration, so this is alpha, angular acceleration, delta omega divided by delta t. So you'll be able to get that now once you get the final angular speed. Just have to get used to these variables. That's part A. Part B is how many revolutions, how many complete paths do you have? So we can figure out the angle that we go through. So these are rotational kinematics equations. So delta theta is omega initial times time plus 1/2 alpha t squared. So we're starting at rest. You can figure out the amount of radians that you go through. So that's the total amount of radians. The question is actually how many revolutions. So you'll get this in radians, whatever this turns out to be, in radians. So a certain amount of radians. And then you have 2 pi radians for 1 revolution. So this will tell you how many revolutions you've actually completed. Okay, very good. Okay, 7.17. Balls are attached to light rods and can move in horizontal circles as shown. And we want to rank from smallest to largest the torques that we see here. So back in chapter 4 and 5, we needed a net force to have a linear acceleration. In the rotational world, we need a net torque to have an angular acceleration. Okay, so let's take a look at this. Okay, so first of all, torque, just in general, is the perpendicular part of the force times the radius, or the perpendicular part of the radius times the force, or another way of saying it is RF times the sine of the angle between those two. So in the first one, this torque, it's just F and R. And these actually have 90 degrees between them, so F times R, that would be the torque for the first one. The torque for the second one, now it's 2F times R. So this one has twice the amount of torque as the first one. So I'll just do the first couple for you. Take a look at the other ones where the radius changes and figure out the torques and then rank them from smallest to largest. But this is the concept behind it. Okay, so next, what is the net torque on this pulley? So here's 20 newtons over here, 30 newtons over here. The 30 newtons make it go clockwise, the 20 newtons counterclockwise, and these forces are being applied at 4 centimeters from the pivot point here. Okay, let's take a look at this. Okay, so here's the picture, 20 newtons here, 30 newtons over here. So with torque, it depends on the force, but where's the force being applied? So if you're trying to open a door, you go to the handle, open the door that way, you get a larger torque than if you were trying to open the door by pushing on the middle or something like that. And remember that torques that make things go counterclockwise are positive. Torques that make things rotate clockwise are negative. So the net torque we have here would be, we've got the 20 newtons making it go counterclockwise. That's positive, so we've got 20 newtons. Distance from the pivot point over to the force would be 2 centimeters or 0.02 meters. And then the 30 newtons actually makes it rotate the other direction, clockwise, which is the negative direction. So 30 newtons, and then same distance to where the force is acting. And the force is perpendicular to the lever arm here. Okay, and the problem doesn't say what is the magnitude of the torque. It says what's the torque. So this actually comes out to be a negative number. And the units for torque, newtons times meters. Okay, next one. In the figure here, figure 1, force 2 acts half as far from the pivot point. So this distance is half as much as this distance. Okay, great. What magnitude of F2 here will cause the net torque to be 0? So we don't want the torque, we don't want this rod to be moving. You apply F2 here, and over here you have F1 at 45 degrees. We want the torques to be balanced. We definitely need a good picture for this one. Okay, so we're trying to figure out the force F2 here, and this distance is half as much as this distance, so that this thing doesn't move. So the torque, because of force 2, has to be equal to the torque because of force 1. And the torque because of force 2 over here would be the force. So torque is force times perpendicular distance. And then this distance. So if I called this whole distance here L, this distance here will be L over 2, which I don't know what L is, but hopefully it's going to cancel out, and you'll see that it does. And then this is going to be equal to torque 1, which is provided by force 1. So force 1 is at an angle here. We want the part of the force that's perpendicular to the lever arm. So F1 perpendicular. And then, so F1 perpendicular times L. So that's the torque making it go this way, equal to the torque making it go that way. It's not going anywhere. Those are balanced. And then you do see that the L's actually cancel out. Okay, so we know what F1 is at 45 degrees. You'll have to figure out F1 perpendicular. And luckily it's 45 degrees. So I call this one F1 perpendicular. That's the part of F1 that actually makes it rotate. F1 parallel, that's my symbol for parallel. F1 parallel does not make it rotate. So for F1, this is the part of F1 that actually makes it rotate. Okay, it's 45 degrees, so I mean, if you pick sine or cosine, it doesn't matter, you'll be correct. But anyway, if this is 45, this here is also 45. And the way I have it drawn, this F1 times the sine of theta will give me F1 perpendicular, right? If that's 45, that's 45. Sine of 45 would be F1 perpendicular over F1. Okay, so let's maybe one more step here. The L's actually cancel out, so I have F2 over 2. This would be equal to F1 perpendicular, which is equal to F1 sine of theta. And then the only thing that you don't know is F2. So F2 would be 2 F1 sine of theta. Okay, great. Okay, so we're going to do a little estimating on this problem. Hold your arm outstretched so that it's horizontal. Estimate the mass of your arm and the position of the center of gravity. And then from this, what is the gravitational torque? Okay, so gravity is a force in this context because the arm has mass. And what is the torque about the shoulder joint? So maybe a little bit of a drawing, and we'll have to do some estimating. So here's an arm. Now the center of gravity of the arm, I'm just estimating it. It's probably not exactly in the middle, but somewhat in the middle. So I'm just going to use this as the distance here, and you could guess whatever it is. I'm just going to say it's about a half a meter. The mass of the arm, maybe about 10 kilograms or so. And then we can figure out what this torque is. This would be the force, which is mg, times the distance to the pivot point r. So when you put all this together, and again, this is just my estimate, I would have 10 kilograms times 9.8 times about 0.5. So when I put all this together, I get, this is about 50 or something like that. So approximately equal to 50 Newton meters. So that's not one of the answers, but the one that has the same order of magnitude is the 15 Newton meter one. I mean, one is down to 1, the next one up is 150. So this is in the same order of magnitude. This would be 5 times 10 to the 1 Newton meters. It's the same order of magnitude as this answer, 1.5 times 10 to the first. So the number that I got here, the closest one would be 15 Newton meters. And I might have over-exaggerated maybe the radius, so the distance to the pivot point a little bit. It's probably less than a half a meter looking at my arm. It's maybe more like 0.25. It's hard to say what the mass of my arm is. I went with 10 kilograms. It's about 20 pounds. Maybe it's a little bit less. Maybe it's a little bit more. But order of magnitude-wise, this is the one that's the same order of magnitude. Next one, an athlete at the gym holds a 1.5 kilogram steel ball in his hand. His arm is 70 centimeters long and has a mass of 4 kilograms. Okay, so he's holding a mass in his hand, and then his arm has mass itself. So we want to figure out what's the magnitude of the torque about his shoulder if he holds his arm straight out to the side. And then what's the magnitude of the torque about the shoulder if he holds his arm straight but at a 30-degree angle below the horizontal. Okay, so I'll do the first part, set it all up for you, and make some comments about how you could approach the second part. Definitely need a nice picture for this one. Okay, so we're going to have to assume that the arm is a uniform shape so that the center of gravity of the arm is right in the center. And that's what I've drawn the arm kind of just like a board. And then the ball is over here at the end, in the hand. So the torque that we have, it's going to be the torque because of this one, ma times g. That's the force. And now the distance from the pivot point over to the force, 0.35 meters. So not only force, but where is the force applied? And then mass of the ball times g, that's the weight of the ball, and then the distance to the pivot point here is 0.7 meters. So when you put all that together, you'll get the net torque. And I think we just want the magnitude. So for part B, you also need a nice picture. So let me just do the arm like this. So this is like a side view. And this is 30 degrees below the horizontal. So here's what we had before. Mass of the arm times g. Here's the mass of the ball times g. So again, we want to get the torques. We're going to have to figure out the perpendicular distance to the pivot point. Now, if you want, you could try to figure out which part of this force is perpendicular, which part of this force is perpendicular to the lever arm. I find in this one it's easier. Extend the line of action of this force, line of action of this force, and this is the perpendicular distance for the arm, this distance here, and again, line of action of the force. This is the perpendicular distance for the ball. This torque goes with that problem. Okay, so if you want to figure out the torque in this situation, and by the way, you'll do a lab that's really similar to this, the net torque here is going to be this force, and then the perpendicular distance to the lever arm. So you'll have to figure out that, actually, the arm one, yeah, this distance here. R perpendicular arm plus mass of the ball times g, perpendicular distance for the ball. Okay, excellent. So you'll see that the torque in part B is actually less because the lever arm is less. So when you have your arm completely out horizontally, like this, there's an amount of torque, but as you bring your arm down this way, it's easier and easier to hold your arm that way. And when you're completely like this, it's super easy. Okay, a small grinding wheel has a moment of inertia. So moment of inertia is a measurement of how hard it is to get something to rotate. So it depends on not only the mass, but also the shape. So a small grinding wheel has a moment of inertia of 4 times 10 to the minus fifth kilogram meters squared. What torque, so tau is torque, what torque must be applied for its angular acceleration, so that's what alpha is, angular acceleration, to be 150 radians per second squared. Okay, so moment of inertia here, what is the torque if alpha is this amount? Now in the linear world, the analogy would be, okay, in the linear world we had mass, force, linear acceleration. We're in the rotational world now where it's not only mass, but what shape do we have? It's not only force, but where is the force applied? How much is the torque? And instead of linear acceleration, we have angular acceleration. So torque is equal to I times alpha, just like the net force was m times a. And then you actually have everything here. I is given and alpha is given. It would be as if they gave you the mass and the acceleration and they said, what's the net force? Here they're giving us I and alpha, and we can get the net torque. Okay, so just getting used to the variables again. You could see it's a formula with 3 variables, and they give you 2 of them. So from that perspective, it's easy. The hard thing to me is knowing what these represent, putting them all together. Okay, so the next one is similar to the previous one. It's just a little bit more difficult. We've got a 250 gram, okay, 250 gram, 20 centimeter diameter plastic disc. So they're giving us a shape, and the diameter is 20 centimeters. Okay, great. It's spun in an axis through its center by an electric motor. So we know the mass and we know the shape. So refer to these pages in the book, and you'll see that there's a table of how to calculate moments of inertia for different shapes. Okay, so what torque must be supplied to go from 0 to 1900 RPMs, and this happens in 4.7 seconds. Okay, let's take a look at this and put it all together. Okay, it does go back to just this formula. Torque is equal to I times alpha. Now, the previous problem, they gave us I and alpha, so it wasn't too bad. Here, we're going to have to figure out what I and alpha are on our own. So the moment of inertia for and I'm going to assume it's a solid disk, is 1/2 mr squared. So they give you the diameter. This would be 0.1 meters. The radius of this shape is half that, so 0.05 meters. Whoops, I got carried away. This is a 0.2, so half of that would be 0.1. Okay, so move it over 2 spots. Diameter of this shape, 0.2, radius is 0.1. So in this one, you have to actually figure out the rotational inertia by yourself. Okay, so we've got that first part, and then we can get alpha. This would be delta omega over delta t, which isn't too bad. We're starting at rest, so we know the initial, well, let me just do one more step first. We know the initial angular velocity is 0. We could figure out the final angular velocity given the amount of RPMs we have here. So this is not the final angular velocity. This is the frequency, not in SI units. We've done problems like that before. So take the 1900 revolutions per minute. 1 minute is 60 seconds. Now this is the frequency, how many things happen per second. And then to get the final angular velocity, it's 2 pi times that frequency. Okay, so again, it takes some work to get I. It's going to take some work to get alpha. And then once you put them all together, you can get the torque. Okay. All right, good. So here we have a frictionless pulley, which can be modeled as a 0.18 kilogram solid cylinder. And we know the radius. There's 12 newtons to the pulling it counterclockwise, 10 newtons making it go clockwise. We know the tensions are 12 and 10. And we want to know what is the angular acceleration of the pulley. Okay, let's take a look at this. So I've just redrawn the picture here, 12 newtons, 10 newtons. These are acting at the radius of the, perpendicular to the surface here. I just, put it over here just to make it a little clearer. Here's the mass, here's the radius. What's the angular acceleration? So same kind of idea, torque. This is the net torque is equal to I times alpha. And we're trying to figure out alpha. So torque over I, that's the net torque, will give you alpha. So first of all, you have to figure out the net torque. This is similar to a problem that we did before. So figure out the net torque, right? It's 12 newtons acting at this distance minus 10 newtons acting here. And you can get the net torque that way. And then you can get the rotational inertia. For this shape, it will be 1/2 mr squared. So the mass is given, the radius is given. So you have to do some work to get the torque, and you have to do some work to get I. So just to remind you, the net torque, this would be the force, perpendicular distance, times r, minus the one to make it go clockwise, 10 newtons, and it's also acting perpendicular here. So same distance away r. So here's how you get the net torque. Here's how you get alpha. Put them both together. Sorry, this is how you get I. Put them both together and you can calculate alpha. Okay, great. Any questions, just email me and I'll talk